This is my turn. I will start with my research interest, which is building a very sophisticated system which can, help assist drivers based on the data science. But so far, for this lecture, I think I can talk about a very clear topics, which is how do we utilize the data circulation system and data science to the behavior assistance in driving situations. Okay. Actually, this is also my first trial to record my whole lectures using PowerPoint software. So also let me give some preparation. Okay, I think that this stuff. Okay, let me title again behavioral analysis using data circulation. So this talk consists of 3 topics. First topic is actually signal processing and its basics. How can we utilize the idea of signal processing? Most of the students of graduate school leading program studied a lot about signal processing. But again, I like to emphasize that the signal processing or system idea is very useful even for understanding the human behavior. And then in the second topic, I like to introduce very old works of our research group, which try to model the human behavior under the real world environment, which is built a mathematical model of driver behavior in terms of signal processing system. And the third topic is how do we build a very useful application system which has driver in the loop of data circulation. And that part of this talk is pretty much, how do I say, premature, and I like have your ideas on this issue, not talk to you, but I hope you will be able to talk to me and input a new idea about future style of driving and future vehicle. So in total, I like to stop my talk in, say, about 1 hour, a slot, and use less of time for discussing about the new ideas about this field. Okay? So to me, many things can be described by signal processing idea, which is the real world is captured by signal, represented by signal and systems. So what we need to deal with is the complexity of the real world. And as you know, signal processing or basic engineering technologies can deal a very limited extent. For example, for the signals which have one dimensionality and supposed to be time sequence, it is not so powerful to describe whole of the complex real world phenomenon. But still, using this, it makes a clear idea of understanding real world. For example, a human behavior can be generalized and simplified by the idea that the human is a system and real world, which is related to the context of the behavior, as well as behavior itself, are signals. So we have 2 signals that represent environment or context of the behavior and the output or behavior itself. And human is a system which converts environmental sensing result onto their own behavior, which must be, for example, rounding the steering wheels or pressing the gas pedals for the driving cases. Well, you can speak as a behavior, or you can, move as behavior. So many behaviors are available for human in response to the context. So this, to me, is a very, very simple signal processing system, which has input and output signals, and in between them, one system, hopefully described by a mathematical representation. So behavior signals are signals associated with human activities. So that is my definition of a behavior signal. And the goal of behavior signal processing is to understand the aims and means and even personality of human beings by analyzing the flow of data, and which again associated with human behavior as well as its context. So, and the third sentence here is that human behavior and context are measured. Here you can suppose that context are very simple signal, but in reality, that is very, very complex signal. So in some cases, you have several channels of signals, and each channel is independent from different channel or dependent in channel, and rate of the sampling. For example, 10 bits per second or million bits per second, those information rates are also different. So this is not a simple one-dimensional signal in actual situations, but the structure here is very similar to me, at least. This is an example of the signals associated with driving. We built this vehicle in 1999. Correct? No, 2004, I guess. Yeah, 2004. Equipped with a lot of sensing devices, which were state of the art at that moment. Currently, these sensors are very old and not so sophisticated. But important thing here is that we capture many things, but those are roughly divided into three groups. One is signals associated with vehicle, and one is a signal associated with environment, one is a signal associated with drivers. Okay? So you can see, for example, video image of the omnidirectional view or 330-degree view is the better or good sensing modality for the environment. And vehicle sensing is pretty much easier than sensing the human, because vehicle is a kind of machine. Therefore, velocity or acceleration, these kind of things are physically measured by sensing devices. And measuring the driver is not easy, because we cannot simplify the human behavior or human being in a simple channels of signals. For example, for the physiological response of the human, we can measure some sort of signals like heart rate or perspiration or maybe skin conductance. These kind of things, we know that these kind of things are heavily related to our internal state, like emotional state or sleeping. I don't know. But actually, it is not easy to measure and to associate these measuring results with the human internal state. That is a big research issue, actually. That's a big research issue, anyway. And I want to talk these kind of things very much, but my time is limited, so I just like pointing out that these kind of things are also measured for human being. Of course, physical movement of the human, which is tightly associated with the pedal pressure. Location of the pedal can be easily measured. but the way of pushing the pedal is so much associated with the human personality. Okay. So by seeing this view graph, I hope you get some ideas about how can we map the real world into the virtual world using the signals. Okay. And you can also see this figure still that is in NIC new building that is located in front of ES building. If you look into the glass in the east side, you can see this vehicle. This is the oldest one among the 4 vehicles there. And to see the situation in more reality ways, we can see video about driving. Actually, it sounds, but I don't know if it sounds. But this is a scene. Driver is talking to the operator who is sitting in the back seat, and she is asked to make change in lane change in left side lane. So she is slightly frustrated with that situation, but she tried to. She's now trying to do that. So she made a steering operation like this, and together with that operation, she again felt some, emotional change, like threat or something. And this case, we could measure some change in physiological signals like skin potential or perspiration, probably associated with this, lane changing operation. So you can see somehow from video, by seeing her face, she must be, frustrated to make lane change, but it is not clear to the computer system. But after, capturing several signals, we can somehow, tell that computer system that she is not a normal, emotional state. And this very important issue for understanding this change of human being. And of course, it is very, very, very difficult. But capturing this real-world scene into the sequence of signal is current technology, and is getting easier and easier and cheaper. And again, the volume of the data gets bigger and bigger. So these kind of things can be, uploaded to the internet world by connecting 1 or 2 LTE smartphone devices onto the vehicle, and using the system that Kisuka-kun developed. I don't know. You can upload these kind of things on a computer in ITC, Information Technology Center of Nagoya University. And every day, every time, every moment, associated with every moment of driving, we accumulate this kind of data. So it's going to be a petabyte or a zettabyte, a huge amount of data. So this is really one of big data. So human behavior and its associated world is very, common to everyone. So the big data are going to be captured by these kind of systems. Okay. So I guess you see how easy to get big data associated with human being. Sorry, I'm not good at operating the surface system. Again, although the data size is very huge, we can simplify the system as a simple data signal system which has input and output. And input and output has some kind of a causality output signal is somehow related to the input signal, and output signal is the result of processing by the system. So there's a causality between two signals. So describing the causality or relation between input and output in terms of a mathematical representation is the problem of the, or engineering problem of understanding human being, which we call human behavior signal processing. Therefore, you may see, particularly the student in a leading program, this is also a very big data problem, and the data circulation will be somehow popping up in your mind by your own weights. Okay, and classically, mathematically, problem of signal processing can be very, very roughly divided into 2 or 3 classes. One class is to determine the system. The other class is to predict the system. And the other class is to determine the system without sensing the input to the system, just only seeing the output of the signal. Output signal, we can somehow estimate the property or characteristics of the system. That is the third problem. And I do not have enough time to talk about this kind of thing in structural manner, and I hope I talked somehow in the data analysis lecture last autumn. I know it was terrible lectures, but I hope you are clever to get something from those lectures. So here I like to emphasize the student from not the leading program student, what you are going to study through the lecture course of acoustic speech and behavioral signal processing will be how to build these kinds of technologies in different modality of signals like acoustics and behavior. Okay, so and this is a mathematical representation that people use. X subscribed by n is a sequential data. Y subscribed by or indexed by n is also another sequential data. And to associate to input and output signal, we usually use Hn as a representation of the system, which we call impulse response. Impulse response. So impulse response is a very simple representation of the system by describing what happens if an impulse is given to the system. So this is an impulse response, and we use this as an inherent representation of the system. And then the input and output relation can be described by a convolutional sum. Convolution. This is a keyword. And if you convert this to a frequency domain, the convolution can be described by a simple product. And things like that. So this is a very basic idea of signal processing technology. Okay? So, yeah. So this is the end of the topic 1. This is the introduction. So do you have any questions or comments on this part? Maybe I want to know your opinion. I'll do it. Yeah, please.
その HN をなんか求めるなんかアイデンティフィケーションってあるんですけど、その運転構造ってなんかどれもなんか似通ってると思うんですけど、でアウトプットからその誰がドライバーかっていうのは判別できるものなんですか？
そう、英語で答えていいSo he asked me if it is possible to identify the driver by just observing or analyzing the output signal only. So yeah, I have a lot of slides to talk about that, but this was a research challenge of Professor Chiyomi Miyajima. I don't know if you know her. She's our assistant professor. And we had measured or recorded about 300 drivers driving behavior. And by only using the 5 minutes gas and brake pedal operation signal, she could tell who is driving in the accuracy above 75%. 75% people in a real driving situation. So that is very interesting topic. So if I have time, I'll talk about that. But if there will be discussions, then you will come and or Miyajima Sensei will talk about that. It's very, very interesting to me. And kind of extension of our old research field. Actually, that field is her PhD thesis, speaker recognition. Speaker recognition is very similar problem. People speak or talk various things, even under the same condition. And by only listening her or his voice, we can somehow have the idea who is talking. That is one evidence that the behavior signal has a personality behind the input and output relation. Okay. So thank you very much for asking. Are there other questions or comments? I like to have objection. For example, the human behavior is not such simple or something like that. I also think sometimes. Okay, so thank you.
Have you ever had the chance to test the models obtained in these experiments?
Well, for example, we verified our hypothesis that the sort of the characteristics of the system is very much associated with the human personality, and the experiment that I showed you was one result that support our hypothesis. And other topic or other way of verifying that system is, I'm going to talk about it later in 10 minutes. So it is not objection, but doubt. Okay.
Or, for example,
Yeah.
have you tried asking to a psychologist his opinion?
Oh. Yeah. The ground truth on the human emotional state is, as you can easily imagine, a very difficult problem for us. Yeah. Because it is inside. Someone say that if you measure the brain activity, you can guess. How do you think about that, Jessica? Can you measure the emotional state of the human?
I think we can determine some specific emotion, but not discern which emotion it is, because there are some things that we can, for example, there are some ganglions inside the brain that we need some sensors inside, so we can determine exactly if they are activated or not. But since when we measure at the outside from here, just the EEG, for example, it's more difficult.
Okay, so the emotions can be converted to signal, but we don't have measure. Am I correct?
not, yeah, not exact.
See. So you have any comment, Sumi-san? You may also working on the emotional state of human. Yeah, yes.
でも私の研究室では暗い運転中の渋滞が起きている時の怒りがどういうふうに感じされるかとかを脳波の測定から判断できているので、どういう方法判断可能かと思うんですが。
So, what is your grand truth? Why you can tell that the subject is in anger or not? In a psychological manner. Who the? Yeah, she's a psychologist, so yeah. You can ask her. how do the people in the psychology? If I have time, I will talk about that. But we had one research paper associated with the frustration, and the reviewer, of course, objected that the way of measuring the frustration is not consistent, something like that. Because we use the self-judged score on a frustration level. And finally, because that was the IEEE paper, therefore many engineers agreed with our reasonable way to evaluate frustration. But someone didn't agree at all. So I think it's very good. So sorry, using your time, and thank you very much for giving us giving me a comment. So I like to go more in detail. But it's very important to understand that something even very familiar or natural to human being, but not easy to measure. That limitation of our current technology. So, okay, this is circulation. We see circulation here. This is the loop of data flow among driver, environment, and vehicle. It's clear. We see we are in some traffic context, and then driver do cognition process and decision process and operation process. Through those processes, we gonna produce some, behavior which can be measured by anyways. And for the driving case, we're gonna operate or maneuvering pedals and steering wheels, and which gonna change the vehicle behavior, and in the context relative to the surrounding vehicles and our road, the traffic situation will be changed. So therefore, very simple loop of signal is characterize the driving. Okay. And on this slides, I don't know how do we formalize, for example, autonomous driving vehicle. Maybe autonomous driving vehicle have missing part of this. Probably they can directly use these contextual information controlling vehicle, and vehicle will change the traffic. But still, in that case, we need to understand we need to understand the data circulation. Probably Professor Suzuki will talk about that, but in order to control the system that consists of different two components, it becomes a very complex problem. We need to both control this and this, but you can hardly control the traffic itself. But traffic, of course, affected by it. So the vehicle controlling problem in the real world is completely complex and each mutually dependent problem. So it's not easy to be learned by simple DNA, maybe as an input. As by using the video signal as input and training a DNA neural network to output these kind of signals. Simply, I don't know. Maybe the result will be shown by Hayashi-kun later. I have not. Okay. So I like to emphasize that this is a flow process and this is a loop of signal. Okay. So I like to discuss a very simple but realistic case. That is car following. In general, if you like to follow the vehicle which is preceding your vehicle, you try to keep the distance to the vehicle in a certain range or distance to those vehicles. And if the range gets longer, you probably accelerate in order to catch up that vehicle. And if the range is shorter than you are hoping, then you decelerate in order to keep the distance. So that is a kind of physical phenomena produced by spring. If you have spring try to keep the length to explain as a natural length of spring. So if you pull the mass, then the force will be induced against the pulling force. So if you pull, the spring pull like this, opposite direction. And if you pull this, push this like this. So this is a very typical motion of equation of the second order, which gives you a sinusoidal signal solution that I guess you study about in undergraduate course if you are engineering student, and sorry if you're not, I don't know. And this kind of, so which means that the solution of a relation between, solution of this signal should be something like this. It's a sinusoidal waveform, or if you're better driver and the preceding driver keeps a steady speed, then hopefully it becomes like damped oscillation. Damped oscillation is the oscillation which which amplitude becomes less as a function of time, like this. So if you pull the mass and release that mass, then the mass oscillate. But in some sense, after some time, a period, I guess, the oscillation becomes a state. So this is a very simple physical system, and you can suppose that the human driving can also be explained by this simple oscillation system. And the other idea is that much more simple way to think that if the driver wants to keep, no, this is not that. If the distance to the foregoing vehicle is getting better, getting larger, the vehicle is getting faster. So this is like a very simple linear relation. Or you probably, a student of the leading programs, studied about the linear regression. So linear relation between the two variables like x and b. And this is another way of thinking. It's very simple way of thinking, and there's no evidence in the physical analogies, but still you can use this kind of simple representation. And sometimes machine learning people try to use this kind of formulation in order to in order to predict the movement or behavior of the human. But anyway, Spring can be described by this, and simple linear regression can be described by this. And if you use higher order regression, of course you can add some higher order terms like this, or you can use Kong. Anyway, how can we choose the model? There's two models, and which is better and which is worse. That is a meta problem. If you choose the model, you can fit, or you can decide the optimal parameter like k or x0 or abc. But selecting the model is not an issue. It's a very difficult, big issue. And it is there are many researches on such meta strategies for fitting the model to the real world problems. And if you are interested in this field, I hope you study better. But my group's idea is to use data and use statistics for finding the knowledge. And the knowledge is not represented like this, much more simpler or sloppy way maybe. Okay, this is okay. So this is a reality. The red line is a trajectory of a real driving situation. The horizontal axis represents the distance between the ego vehicle and preceding vehicle, and the vertical line represents the velocity of that vehicle. So as you can clearly see that there is a simple tendency of the linear relation. If the vehicle's distance gets longer, then the vehicle drives faster, and things like that. And of course, and you can hardly see the trajectory like this. Oh, what is this? I did not mention much about the rounding trajectory on this field. Actually, sorry, I need to go back to my previous slide. Actually, I need to talk a little bit more about spring oscillation problem. If this is spring and obey this equation of motion, then the solution would become like this. This is a kind of a sinusoidal signal, and if you calculate the sinusoidal signal, calculates the time derivatives of the sinusoidal signal, it becomes also sinusoidal signal. So if you plot a joint plot of distance and velocity, then the trajectory becomes a circle. Or if the signal is a damping oscillation, then it becomes like this, falling into one point, which is known as the attractor of this system. Anyway, so this shape in this plane, actually this is called the phase plane. Phase plane is x times x dot. The relationship between location or displacement and its velocity is called phase plane. And if the solution of this system is kind of a sinusoidal signal or damping sinusoidal signal, a trajectory in this on this plane becomes like this kind of shape. So this is a very interesting analysis way of moving systems. And again, you see here, you come here. Here's a simple linear relation, but not exactly it describes all of them. And you can also see some rotational trajectory, but that is not a big one, but a very small one like this, which means that locally the model of the damping spring works, but it doesn't represent the global movement or global behavior of the driver. See, here's curls, and here's a curls, and here's also curls, but there's no big, rounding trajectory. In globally, linear regression looks a little bit better than fitting the damping model. So this is a combination of multiple states system. There are several systems here, 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 here. And by looking onto each system, you can clearly understand that this is a kind of damping oscillation phenomena, and that can be easily modeled by K, which is a damping, spring constant, and XL is the natural length of the spring. But it is not always the case. There's no big spring, but there are a lot of springs. Okay, here spring, there spring, here spring. So we have a lot of springs here under the real world situation. So real world usually consists of many, many different systems and states. And each of the states can be represented by a very simple system like spring, but the whole of them is not such simple. So how can we do that? How can we deal with this? What we can use is data. We have not so far fully utilized data distribution. If you use, or if you have had a lot of data, what we can do is you can estimate the distribution of data as accurate as possible, as the size of data increase. So let's see that this is not a simple function, but see, this is a set of values, two values. They are displacement and velocity. And see that we observed the joint distribution of two variables. Okay? Then what you will see is something like this. There are several mountains, and there are several platoons or ocean here. Of course, the height of the mountain represents the frequency of the observation. So in this part, we can somehow get idea. There is a local state which is separated from the different state. And in that state, we can observe the simple circulating or simple rounding movement which has the different attractors in this plane. So this is very interesting idea to me. Using data distribution in order to represent the physical problem. Do not use explicit form like linear regression or damping spring system model, but just calculate the joint distribution. Will gives you some idea about how the system behaves. So this is a fundamental idea of statistical signal processing. So where do you see input and output? Yes, this can be input, this can be output, or causality, becomes meaningless or less meaningful in this case, because joint distribution is completely asymmetric with x and y, x and b. So we can replace these two things. We will have also the same distribution, our same look distribution by observing the same phenomenon. Okay, so how can we use this kind of joint distribution, which is measured by a real world, as a knowledge source without building a mathematical model? That is a key issue so far at this moment of this lecture. Okay. Again, this is depicting that there's a local system and global trend. Local systems and global tendency. So the combination of this is okay, and this is it's a very simple review of joint distribution, or which, in other words, joint probability. So here's a TV guy. He's asking a pedestrian if you like dogs or cats, and also he records the pedestrian. The person is male or female. And finally, they got these numbers. This is called joint distribution of two variables. One variable is the type of pet, and the other one is gender. Okay, so there are two freedoms. One is pets, cat and dog, that is binary, and the other one is gender, that is also binary. This is a cross table, but this is actually joint probability. Joint probability is a set of numbers which represent two stochastic things happens at once. I mean, probably the probability that a sampled person prefers dog is 0.28, because the dog preference of female is 10 and male is 18, therefore in total 28 persons prefer dogs. So the statement here is that the person prefers dog, regardless with gender of the person, is 0.25%. This is known as the marginal distribution, actually, in terms of the probability theory. And the joint probability is like this. The joint probability that a sampled person is male and prefers dog. So sampled person is male and prefers dog is 18. So here 0.18 is mean that 18% 100 out of 100 subjects prefers dog and male. Okay? And the conditional distribution, that is key. That is key idea of building the human behavior system, to me at least, based on the data circulation or big data analysis. That the conditional probability that the sampled person prefers dogs when the sampled person is male. So you knew that the sampled person is male before asking the preferred pets. Then the probability that the person prefers dog to cats is 0.90%. 0.9. So this is a great change of probability comparing to 0.28. Without knowing the gender of the person, you can net. You estimate that 28% he prefers dog. But after knowing that the person is male, then the change to almost 90%. So the change difference of this and this is a very important knowledge source. Just knowing, what I like to say is just knowing this cross table is enough to predict or change or differentiate the preference of the subject. So knowing joint distribution allows more accurate guess. That is the point. Of course, there is many exceptions. For example, if you ask, for example, the dinner menu last night together with pet preference, what you will have will be less than the gender, the case of the genders, because gender is more related to the pet preference than yesterday's dinner menu is, which is sometimes referred as the joint distribution, dependence of two stochastic variables or mutual information measure for measuring the mutual relation between two information sources. But anyway, you see, by knowing this gender here or there, you can differentiate the prediction result like this. And this is very simple, description of the joint distribution and conditional distribution, and in complex math form or continuous distribution case like driving behavior, we can use another way of representation, which is kind of a second order polynomial, which is on power to the natural log's base e. But this is not important. The important thing is that if you know the distance, then the distribution of the velocity changes a lot. If you know that the following distance is, for example, 10 meters, then the average of the velocity becomes like this area, maybe 7 meters per second or more. But if you knew that the velocity is 20 meters, distance is 20 meters, then the expected distribution of the velocity has mean value of 20 meters per second or something. So by knowing this joint distribution gives you some idea of estimating or predicting the velocity from the following distance. This is causality. This is the cause and this is the result. And if you use this as an input, then you can calculate that and this as output. So this can be implemented in a big box data signal system by calculating the most probable value or average value or mean value. That's not so much different based on the observation of the different value. Okay, so this is the second topic. How can we use the data and evaluate the data as a knowledge source? And these are typical and a little bit classical ways of understanding the complex distribution like this. In this case, for example, there are actually 7 or 8 mountains on this plane, and which means that we can mathematically describe this by summing up 7 or 8 Gaussian distributions, which may be characterized by the equation like this. The weight times Gaussian distribution gives you a probability that you observe the set of data. And also, you see what here is that there are a lot of peaks. If you use a simple distribution, you get only one peak, which means that the input and output are not so much related. But you have several peaks distributed in a phase plane, then you can get more complex but more flexible representation of data. And if you expand this idea to the time direction, Markov model is very useful. Markov model is a model which has multiple states, like multiple distributions, but each states are connected by a directional line, directional path, or arrow, in other words. So you can move from here to there, from here to here, by by observing or by injecting the sort of the stochastic value or signal. So after this state, you can only be here or here. After this state, you cannot go back to this state, but to the right state, or stay in the same state. So this kind of time sequence can be, characterized by several states, and each state has a data distribution. So again, please go back to the this fundamental figure. We have several states, and if there is time progress characteristics behind this distribution. For example, if you start here and here and here and here, or something like that, then we can also use a hidden Markov model as a time sequence representation of data distribution. But this is a very tiny thing. Please remember that anyway, two very useful technologies. One is Gaussian mixture modeling, and the other one is a hidden Markov model. Okay, so I guess this is the end of, this is the, what we are doing now. So, one simple question, how many states do we need to describe the real world driving behavior? How many? I'd like to know your idea. How do you think? Oh yeah, so sure. Yeah. There are a lot of states associating with driving. Intersections, highways, rainy, pedestrians, parking vehicle, blah, blah, blah. Yeah.
If you want to let me just say the number that is hard, but I think at first, according to the different road, like highway or the way from the downtown, the way from the far away from the country, and it also depends on maybe the weather. Is it Sunday or it's sunny?
You're right.
Sunny or rain. And maybe also about the traffic. There's lots of car on the road, or there's almost just walking man, something like this. So, yeah, but I'm not sure how effective it can be. Maybe it should be discussed for a long time.
Yeah, I'm not sure neither. So, Kitsukawa-kun, do you have any idea how many states do we need to control the vehicle? Depends on each state.
I haven't think about that, but I think more than 100.
Sure, of course. Not such number to me. Well, my, scientific curiosity or question is that if the number of the states is more than the information variation that given by this resolution of an image. Suppose that this image has, for example, 100 megabyte, which means that 2 powers to the 100 different images can be exist. So that's a huge number, right? Is it more? Do we need more states for controlling the vehicle under the all real world than the variation number of this kind of resolution of image or not? That is my current biggest question. Because I was working in the speech recognition field, and speech has only, for Japanese, for example, 100 syllables, only 100 syllables. In terms of phoneme is more smaller acoustic unit of language, less than 40. But speech current recognition system trained by Google, for example, uses more than 100 millions of states to represent such acoustic variations. So I don't know why do we need such a large distribution, but there's a lot of people living in this world, like 1,000 million. And we have many languages, and we have many communication line qualities. I don't know. So variation of human activity is huge. So training the system requires a huge amount of data based on this kind of simple representation. So my question is that it is possible or impossible? And if it is possible, I think I go this way. Making the human behavior very, very simple manner that has a huge amount of states, and get data as large as possible, as many as possible, and use those to train that model. That is what Google did in speech recognition field. Another way is to build a very sophisticated mathematical model which can represent almost safe human behavior by several set of parameters, which can be tuned carefully by human manual operation. So I think there are two directions, and my direction is somehow, close to the Google's way. But this is a mathematical fundamental idea, and real issue is the issue of volume of data and how can we train this complex system. Okay, I hope you could get my, or have, have shared the feeling of how to train the complex system. But okay, wait. So this is an example of our result, which utilize the joint distribution of intervehicular distance and its velocity or pedal position, and estimate the pedal position of the 1 second later by utilizing the joint distribution and maximizing the distribution, for selecting the maximum probability value as a prediction result. By the way, this is the result or profile of two different drivers. Driver A is a very lazy driver to follow the vehicle, foregoing vehicle, and driver B is very, and he tried to keep the distance constant very carefully. Therefore, he keeps the intervehicular distance like this, but driver A didn't care about the distance. And as a result, driver B hit the pedals very frequently in order to adjust the distance, but driver A didn't do that so much. So these things are observation result, and we can build the joint distribution of this and this, and calculate the most probable prediction result, and which is end up with like this. This is the blue line, maybe, the prediction result by just using the joint distribution. Red dotted line is the original one, and you can see that almost, it's a very good prediction, right? At least the individual distance is accurately predicted by our method, and the difference between two drivers are clearly shown in this figure. So what we have used was simple Gaussian mixture model, and the difference between two systems are the mean and variance of the Gaussian mixture system. In other words, just the joint distribution is not same, but other things are fixed, equal, and we can characterize the difference of the drivers. So that is one evidence of that we can somehow characterize the personality of driving using the data distribution. Okay, and we can extend this system to much more complex system like changing behavior, and that is also be able to modeled by Hill-Markov model. Okay, so okay, so this is the end of the second topic, and I have used much longer than I expected. Therefore, I just like to talk about, or just like to ask you about your idea about future direction of our research. Okay, so so far we can build a good mechanical system which is controlled by software. In other words, they usually use the word cyber-physical system in order to assist the driver in many contexts. But it needs intelligence. It requires intelligence to assist the human driver, because without the good sensing system or good predicting system or good planning system, we cannot show what would be the optimal operation under the given context. Okay, so building this is currently the biggest issue of our research group. Of course, many people are trying to utilize various levels of knowledge in order to, realize the fully autonomous driving vehicle. So without driver, this line. Yeah, this is very interesting challenge. But to me, we need more intelligent system in order to realize much more useful and valuable driving assistance systems. And the issue is that we need to handle different types of knowledge, not only physical knowledge, but also legal or cultural knowledge on the driving. And also empirical knowledge is very important for the naive driver. It is clear that the naive driver is doing worse than the expert driver who has long history of driving. How can we represent these kind of things in the way of computer understandable representation, computer understandable way? Because what we need to train is a computer system or information system. They do not know the idea of the legality or regulation or social customs. General driver, easy to go over the center line when the bus is stopping in the left side of the big road. But if you hardly code that, you cannot go past the center line of the road. Then that vehicle cannot do anything if the bus is stopping in front of you. And the vehicle stops behind the bus and waiting for a long time. Even the bus is in order and keep stop. So we have a flexible ability, which is known as intelligence, to combine these different knowledges associated with traffic or driving, and select the optimal answer. And the optimal answer depends on the situation or depends on the people. So knowledge representation manner is very, very difficult. And to me, still having a lot of states for each, corresponding to each situation, and train every situation by utilizing the huge amount of data is the shortest way. Otherwise, we need to build a complete AI system, like a, Knight Rider, or like a Terminator, I don't know. Well, it's not realistic to me. What we can do is to import our social knowledge onto the hardware system, which is completely under the control of our mechanical framework. And porting the social knowledge should be done only by collecting the huge amount of data associated with our social behaviors. So this is my hypothesis. So I wanted to discuss about this thing, but I'm afraid that time is up. So again, in terms of the data distribution, of course, we can train this intelligence by using the actual history, driving history, which is captured by data, and train this more and more, wiser and wiser. But important thing is that we need to impose a value to this intelligence. Otherwise, intelligence cannot grow. For example, if you use a lot of traffic data in order to control this system, that system will behave pretty much like a human driver, which means that he cause the traffic accident. And every year, certain numbers of people will die due to the bad driving manner, because bad driving manner is also recorded as a human behavior. So we need to impose value in order to select the better driving or safer driving to the bad driving or dangerous driving. That can be done only by a human being. So I think I used almost time for this lecture. But I still like to have several comments or questions from you. So if you have any questions or comments, please raise your hand. Or you're tired? Actually, this is the second class, of this morning, so I'm pretty much tired. Tired enough to end this lecture now. So it's okay? Okay, so thank you very much for joining. And we have some announcements to the reading program students. You have assignment. But I'm not correctly remember. Yujima sensei, do you have any comments on the assignment? I have not. So you need to submit report, and that is instructed through the email.
Yes, for reading from a student, please
I have already sent the format of report. So please send it to Office Core at MacRWDC to next Tuesday.
Office core.
Office Core at MacRWDC.is. And is there any student who take this class? 世界データ循環システム特論 Is there any student who take the 世界データ循環システム特論 without an electron student? You. Okay, so after this class, let's talk about the report or credit.
Okay, and the students for the acoustic speech and behavior signal processing for media science department, please go to number 7th building next week. That will be held in the first floor or second floor of the 7th building as scheduled. Okay, so thanks very much.